Welcome to qnawire.
Okay, in this problem we have a liquid cesium sample that we're superheating to produce an atomic beam of some kind. It's kind of interesting. The temperature of our oven is about 400 degrees Celsius, and it's about 55 cubic centimeters. The vapor pressure of the cesium will be 17 millimeters mercury, and we're given the diameter of the cesium atoms, which is about 0.33 nanometers. In parts A, B, and C, we're asked to find respectively the root mean square velocity, which we can just get from kinetic theory. And then we're asked to find the frequency that an individual atom collides with other atoms. So we're going to call that F sub C. And then we're asked in part C to find the total frequency of all the atoms colliding per second. So a number of collisions per second total in our sample. Okay, so to start us off, the root mean square velocity is given from kinetic theory. It's root 3 kT over m, where k is Boltzmann's constant. We have the temperature of our sample, and m is the mass of the individual atoms. An equivalent expression is root 8 kT over pi m, this is equation 18-7b. So just plugging everything in, we have, remember our Boltzmann constant is always 1.38 times 10 to the negative 23 joules per Kelvin. The temperature in Kelvin, it has to be in Kelvin, 673 Kelvin. That's just 400 plus 273, which is how we do the conversion. So we have pi times 133 times 1.66 times 10 to the negative 27 kilograms. Okay. And crunching the numbers, the root mean square velocity will come out to be about 330 meters per second. It's actually 327.3, but it's good to approximate it up to something nice. All right, now to get a collision frequency, we need to get the mean free path, which is the distance a individual atom will travel before it makes a collision. We'll combine this with the ideal gas law. So to start, the ideal gas law, PV equals big N kT, and it's the total number of particles in the gas. K is Boltzmann's constant as usual. We need to get N over V, which is P over KT. We're going to use this for later because the traditional expression for mean free path involves N over V. And that actual expression is kind of gross, to be honest. 1 over 4 pi root 2 r squared, where r is the radius of the individual particles, times N over V, which you can see we're going to replace N over V by something involving pressure and temperature instead. And so once we make that substitution, we get KT over 4 pi root 2 r squared times P. All right. At this point, we can plug in Boltzmann's constant, temperature, the radius of our particles, which we're given, right? And the pressure, which we're also given in millimeters mercury. So let's actually, it probably would be useful to actually put these numbers in because there's a little bit of nuance in how we're doing these units. It gets a little gross. Boltzmann's constant is as usual. Temperature is as usual. 4 pi root 2. Remember, the radius is half the diameter. That's a common mistake, because we have to use half. 1.65 times 10 to the negative 10 meters squared. Our pressure, 17 millimeters mercury, needs to be converted into pascals, which is 133. Sorry, I'm almost out of space here. 133 pascals per 1 millimeter mercury. I'm not going to include that. All right, so we're completely out of space. But once we compute it, the mean free path comes out to be about 8.49 times 10 to the negative 6, so about 9 micrometers. Okay. Now to get a frequency of collision for an individual particle, we take its mean free path, or rather we take its average velocity divided by this mean free path. A velocity divided by a length gives you a frequency. You can check the units. It's going to have units of inverse seconds. The speed is just the mean speed, which we already calculated in part A, 327.3 meters per second, divided by our value for the length scale, 4.9 times 10 to the negative 6 meters, which gives us, drum roll, about 3.9 times 10 to the 7 collisions per second. It's a lot of collisions. We're getting a ton of collisions per second because the mean free path is so small. So it barely goes any distance before it collides with things. And this is typically the case with a gas, especially when it's at higher temperatures. Okay. Now for part C, it's not much different, except the total number of collisions is going to be the total number of atoms times the frequency for an individual atom, or individual molecule rather. So just big N times FC. And there's a little bit of nuance here. Because collisions involve two particles at a time, two molecules colliding at a time, we have to add a factor of 1/2 in here, or else we're double counting. So it's really half the number of molecules times the collision frequency. We use the ideal gas law to find big N in terms of things we actually know. So big N is really just PV over 2kT, or rather just kT, times FC. And we can plug in pressure, volume, Boltzmann's constant, and temperature as we've done in parts A and B. And remember, we need to convert to pascals to make it work. So we have to do what we did in part B. Just remember that with pressure. And once we do that, we will get a result of 2.6 times 10 to the 26 collisions total per second, due to all of the molecules in the sample colliding. And that's it. The hardest part of this problem is converting your units properly, and also noticing that to get a frequency, all you have to do is divide a velocity by a length scale. That's really the only difficult parts that I can see in this problem. The rest is just applying the equation for the mean free path and the expression, the ideal gas law. And that's really